Okay, gang, this is the beginning of lesson number 2 in our EKG series. In today's lesson, we will talk about measurements and time, and we will name the segments of the cardiac cycle. And we'll talk about some fundamentals that we really need to know as we move into the rest of the cycle. So what we're going to learn today in this lesson will hopefully really set the foundation for some of the things we'll be doing later. Before we move into lesson 2, I want to do a quick review of lesson 1. And if you recall, in lesson 1, we talked a little bit about conduction of the heart. And so, as we've all agreed upon previously, I am no artist. I didn't go to art school. And so here we get a stick figure heart, but it's going to serve its purpose well. So right up here we have our AV node, our SA node, and that's the sinoatrial node. Right here we have our AV node, okay, the AV node. And as you recall, the SA node typically is responsible for being the pacemaker of the heart, and as it sends off electricity, it's going to come down and it's going to come across, and it's all going to make its way right here to the AV node, and it's going to be slowed down just a little bit, usually less than 200 milliseconds. Okay, so the AV node is going to slow us down less than 200 milliseconds, but it's going to slow us down just a little bit, and then we're going to come down here through the bundle of His. All right, we have a right bundle and a left bundle, and then into our Purkinje fibers and the ventricles. Also of note from our first lesson is to remember that our different parts of the heart have different intrinsic rates. And this turns out to be very important as a clue later down the road when we're looking at cardiac dysrhythmia. So remember our sinus node, which is right here, the pacemaker of the heart, usually is going to beat 60 to 100 times per minute. The AV node is going to be 40 to 60 times a minute. And then down here in the ventricles, we're going to be 20 to 40 times a minute. And most of the time, we're going to see that as a rate of 30. So remember, it's important to think about those intrinsic rates because, as we talked about before, cells have the ability to act as pacemakers. So they can initiate electrical conduction, but they can also, they can take over. They can have sort of an escape rate. So if for some reason the SA node fails and it isn't putting out electricity, well, then any of these cells could potentially do it. But at a bare minimum, the AV node can pop in and say, well, I'm not getting conduction 60 times a minute, so there might be something wrong that I need to take over. And similarly, if the AV node is broken and there's nothing getting through it, then the ventricles will say, well, I'm not getting electricity at least 40 times a minute, so I'm going to start making my own, which will usually be a rate of somewhere around 30. Okay, so those are the important topics from lesson 1 that will set the stage for today's lesson number 2. So the first thing we need to do in this lesson is talk about some basic terminology that is going to stick with us through the remainder of our ECG course and forever and ever whenever you discuss ECG in any way, shape, or form. And one of the things to consider when we learn ECG is that really it's like learning another language, and the way we become familiar with other languages is to practice vocabulary, to use that vocabulary in context, to review the vocabulary, and ECG is no different. So let's talk about some basic terminology that is going to stick with us. Okay, so what you have in front of you here is a standard piece of EKG paper. And usually on this EKG paper, there will be some writing that you'll see up in the upper part of the paper. And that writing is usually the computer's interpretation of the EKG, and usually it's going to include some measurements regarding the different segments of the EKG. So we're not going to get into this part of the paper until we get into 12 lead ECG later on in the course. But what I do want to start out with is helping you understand what is going on this paper. And so this paper, just like any other graph paper that you're familiar with, it appears in two axes, right? So we have this up and down axis, which is the y-axis, and then we have this axis going this way, which is the x-axis. Okay, so along the x-axis we have time, and in this y-axis we have size. So we measure size in millimeters, where every little box is a millimeter, and we measure time in milliseconds, where every little box is 4D milliseconds, 40 milliseconds. Another way to think of 40 milliseconds is 0.04 second, or 4/100ths of a second. So what that means then is, if we zoom in on this, every big box, which is the size from there to there, is made up of 5 small boxes. Okay, 5 small. So if I have 40 milliseconds and I multiply that by 5, I get 200 milliseconds. So each one of these long boxes is 200 milliseconds, or 0.2 second. Okay, so little box is 0.04, big is 0.2. Otherwise, we'll say they are 40 milliseconds or 200 milliseconds. So let's see why this is important then. So because I know the distance between boxes, that means the following. Let me get a little bit smaller pen to write with. So if I have something that starts here and takes up 5 big boxes, 1, 2, 3, 4, 5 big boxes here, I know this is equal to 1 second of time. And I know that if something takes up 1 second of time, because there are 60 seconds in a minute, this is equal to 60 beats per minute. So some other ways you can think about that, if you're so inclined, which is probably a lot easier than what I just showed you, is you can take 300 and you can divide that by the number of big boxes. So in this case, if we divide that by the number of big boxes, that's going to be equal to 60. Similarly, if we only had 2 big boxes, so we had 300 divided by 2, then that's going to equal 150. So this becomes important to know when you're trying to figure out rate by eyeballing it. Something else you can do is you can take the small boxes and you can use 1500 as your numerator. Okay, remember the numerator is the number on the top, denominator is the number on the bottom. So if you want to count small boxes, then you could get even closer with regards to your accuracy. So in our example here then, this is 25 small boxes. So 1500 divided by 25 should again be 60. In this one, this is 10 small boxes. So 1500 divided by 10 should again be 150. But let's say you wanted to do something a little different, and you've got a couple of big boxes, and then you've got 3 little boxes here. So you've got 13 small boxes. Okay, so $1,500 divided by 13 equals 115. So when I tell you all those things, we make a couple of assumptions, and the assumptions are really pretty simple. And by a couple, I guess it'd be more fair to say we just make one assumption. And the assumption we make is that as the paper comes out of the machine, it comes out at a rate of 25 millimeters per second. Okay, and we know that to be true because I just told you that one box is 200 milliseconds. So 1, 2, 3, 4, 5 boxes makes up a second, and that's equal to 25 millimeters. So since we know that the paper comes out at 25 millimeters per second, and since we know how to calculate heart rate, there are some assumptions we can make then when we're looking at intervals for rate. So notice right now I haven't done anything about EKG components, and all we're talking about is just measuring time. So again, I'm going to zoom in here. So if I have something that goes from here to here, and that is one big box. Remember what I told you before, so 300 divided by the big box. I know this rate is going to be 300. If I have something that goes from here to here, I know this rate is going to be 150. If I have something that goes from here to here, this rate is going to be 100. Similarly, if I have one that goes from here to here, 75, here to here, 60, here to here is 50, and then here, how many boxes is that? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7 boxes. 40. And then this next one will be around 38. And then this next one, 33. And then this next one here is going to be 30. So in general, you can remember, and you'll get in the ballpark if you say 300, 150, 100, 75, 60, 50, 40, 30. And that's really the 30s, but it'll get you in the ballpark. And the bottom line is, once you get in here and you're going slower than that, this is too slow. And if you're going this direction, it's too fast. So again, all of that assumes that you're looking at paper that is 25 millimeters per second, and in the setting of 25 millimeters per second, one big box is equal to 200 milliseconds, or 0.2 second. And if you can remember that one big box is made of 200 milliseconds, then you can figure out time from here on out with regards to the ECG. So here in a minute we'll circle back around and I'll show you how to use that information to actually calculate rate other than the theoretical that I just showed you. But before we do that, we need to understand how it is that we identify portions of the ECG and what it is they represent. So in general then, if we have a segment, it's going to start out with a straight line, and then it's going to have a little ditzel called a P wave, and then a little bitty space before the start of what's called the QRS complex, which is going to look like this, and then back to baseline, and then a T wave, and then back to baseline. So for the sake of argument then, let's identify these different components. So when I have the straight line that we're referring to as baseline, which is this line and this line right here, I'm just going to put a little parenthesis around it, that's called the isoelectric line, and I also refer to it as baseline. And so you'll hear me talk about baseline, and when I talk about baseline, I'm talking about the isoelectric line, which is the point where we have no electrical activity. So remember from lesson 1, we talked about myocardial action potential, and we talked about right before depolarization, when everything is neutral, we're actually sitting at a negative voltage, and that's going to be equal to our isoelectric line. This next ditzel right here, this is called the P wave. So the P wave represents atrial conduction. Okay, so P wave equals atria. And most commonly when we think of the P wave, we think of it as coming from the SA node. Okay. For the sake of argument right now, let's just believe that to be true. So then the next thing we have is what's called the PR interval. And intervals are typically identified with the letters and then a line over it. So the PR interval is the start of the P wave to the beginning of the QRS complex. Okay, that's the PR interval. So that's the start of the P to the start of the QRS complex. And you don't have to remember this right now, but as we will learn later, the normal PR interval is less than 200 milliseconds. And what the PR interval represents is, think of it as what's going on at the AV node, where the AV node very so slightly slows down conduction on our way into the ventricles. Speaking of the ventricles, the ventricular depolarization is represented by the QRS complex right here. So remember, when we're looking at the ventricles, remember we have atria up here and the ventricles down here. You have two ventricles. You have the right and the left is bigger, and the left is going to have more electrical depolarization than the right. So one of the things that is important to recognize is when we're looking at QRS complexes, think of it similar to this. So let's say you have an electrical vector going 8 units this way and an electrical vector going 6 units that way. You'll get a vector going this way that is 7 units. It's the average of the two. So one of the things that is easy to overlook when we're studying ECG is that this is actually a three-dimensional object, and so we have electricity going from all sides of our three-dimensional object. So what happens then is the lead and I'll talk more about what a lead is in just a second, has to take the electrical activity and average it in order to give us something we can see on the paper. So I cleaned this up a little bit, and I did that so I could show you the rest of the components here. So at the end of the S, and right before we hit our T wave, we have the ST segment right here, and then we have our T wave right here. And T wave represents repolarization of the ventricle. Okay, and it's a very important distinction because you might be asking yourself, well, where is repolarization of the atria? The answer is that it's buried in my QRS complex because it happens at the same time as ventricular depolarization. So the T wave represents repolarization of the ventricle, and remember we talked about when we talked about the action potential that there are two different periods of time called the refractory period, and one is called the absolute refractory period and the other one is called the relative. And so the difference here is during the absolute refractory period we have not repolarized the cell enough that it can be depolarized again. So we think that the absolute, well, that was a terrible drawing, the absolute refractory period is going to happen somewhere in the first half of the T wave, and then the relative refractory period is going to be over here in the second half of the T wave, which means we're not completely repolarized, but we're repolarized enough that we can go ahead and cause depolarization. And we'll talk about at some point later why that might be important to recognize. Alright, so the last thing I want to show you in this lesson is how we kind of put some of this together. So I pulled this up off the internet because, well, let's face it, they do a much better job drawing than I do. But what I wanted to show you is how we use the information that we've learned today to understand what's going on. So right here where my pointer is, this is the P wave. This is the QRS complex here. And then this is the T wave. And then with regards to rate, here you can see what they've done, where they've taken a QRS complex that's on top of a thick square, and then they've counted to the next thick square, and that's how they come up with the rate. So in this case, 300 divided by 3 is 100, or 300 divided by 5 over here is 60, where there are 5 big boxes in between our QRS complexes. So I know right now this may be sounding a little esoteric, but if you just sit down and play with it for a couple minutes, it'll make a whole lot of sense and it'll come right to you. I think in general, I typically use the 300, 150, 175, 60, 50, 40 rule, but there may be some times when you may have a test question on an examination or a registry exam or any of those kinds of things where they expect you to use the 1500 divided by small boxes rule that we discussed. That way you get a little more accurate heart rate. So gang, that's it for this lesson. Next time in lesson 3 we'll talk about sinus rhythms and how to identify those. Take care.